All right, 8th graders, we are now in Chapter 5. Chapter 5 all talks about properties and attributes of triangles. So in this section, we're going to talk about perpendicular and angle bisectors. Now, the great news is that the actual concepts of perpendicular bisectors you've learned before, but we're going to put them into theorems and make it just a little more complex than what we've done in the past. So 5.1, perpendicular and angle bisectors. Who uses this? The suspension and steering lines of a parachute keep the skydiver centered under the parachute. Hence, if the diver is hooked to the strings, they're equidistant to where they connect on the parachute. Which leads us to our first vocab word. When a point is the same distance from two or more objects, the point is said to be equidistant from the objects. Triangle congruence theorems can be used to prove theorems about equidistance points. Before we go any further, I want you to think of a circle. If you have a circle with center C, all of the points around that center, which actually would represent the radius if you connected the center, but all of these points are equidistant. That is what equidistant means, but it's only for when you have the same distance from two or more objects. All right, we are talking about the distance and perpendicular bisectors. So you've already talked about perpendicular bisectors in the past. Now, one of these is the perpendicular bisector theorem. The other is its converse. Pay close attention to the hypothesis and conclusion. I'm hoping by now, when you guys look at the hypothesis, that's what you're given in the problem. Your conclusion is what you are proving. So, here is what the perpendicular bisector theorem states. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So it says this: if you have a point anywhere on this perpendicular bisector, and in order for something to be a perpendicular bisector, we would have to form 90-degree angles, and the two pieces would have to be congruent on either side. Hence, like here, point Y would have to be the midpoint. Anywhere on this line, this perpendicular bisector, if we have a point, it is equidistant to the segments at the end of what it bisects. So for example, this point, in this case point X, it is the same distance here and here. Now you could have had a point here. This is the same thing. Those would be the same distance. So your conclusion would be that the lengths are equal. The lengths are equal. Hence lengths. Not segments, lengths. Converse of the perpendicular bisector theorem states this: if you know those two segments are congruent, hence which means they're equal, then we know two things. We know that segment YA is congruent to segment YB, and that segment XY and segment AB are perpendicular. So we know then it is a perpendicular bisector. So the perpendicular bisector theorem is when you have the perpendicular bisector, it tells you the segment on the perpendicular bisector is the same distance from both endpoints, and the converse says the opposite. If you know those segments, those lengths are equal, then we know that the line is a perpendicular bisector. All right, now this proof, you do not need to write this entire proof down at all. I just want you to pay attention. This right here is proving the perpendicular bisector theorem. You're never going to have to do this again because you're actually just going to use the perpendicular bisector theorem. So look at what you're given. If you're given that line L is the perpendicular bisector of AB, and you know that segment AB and segment AY and YB are congruent, we can prove that XA and XB are equal. Here's how. Since L is the perpendicular bisector, then we know that this is the midpoint. By the definition of midpoint, we know that segment AY is congruent to segment BY. By the reflexive property, we know that xy is congruent to itself. So we know this triangle is congruent because of side angle side, because we know the right angles are congruent. Because of CP/CTC, we know that XA is congruent to XB, and because of definition of congruent segments, we know that XA and XB are equal. Now at the bottom, you do need to write this down. A locus, not a bug, is a set of points that satisfies a given condition. The perpendicular bisector of a segment can be defined as the locus of points in a plane that are equidistant from the endpoints of a segment. Now you're like, I have no clue what that even means. Here is what it means. If you had this segment AB, if I have a set of points, and let's say this point, this point, this point, this point, this point, and so on, all of these are equidistant from the endpoints. So this distance is the same as this distance. This distance is the same as this distance, and so on. If we actually made all of these points connect, we have just created the perpendicular bisector. That's what it states, is a locus is a set of points that satisfies it. You could say a circle is a locus. All of the points around are equidistant to the center, so if you actually put all of these points together, you would make a circle. You could say a circle is a locus. So let's look at example 1. We have 3 parts of this. We just want to find the lengths of all the sides. So in example 1, find each measure. A, YW. Here's YW. Because we know XZ is congruent to ZY, and we have a perpendicular bisector, we know that segment WX is congruent to segment WY, which means their lengths are equal. Therefore, YW would equal 7.3. BC, we want to find the length of BC. Because we know these two sides are 36, we can say it's because of the converse of the perpendicular bisector, and the converse of the perpendicular bisector, we know that because of the definition of segment bisector, if something is bisected, this would also be 16, and therefore the distance would be twice that, which is 32. So BC would equal 32. And lastly, PR. Since we know that we have congruent pieces here, and we have a perpendicular bisector, we know that 2n plus 9 would have to equal 7n minus 18. And if we solve that, we would get 27 divided by 5, which is 5 4/10. So the value of n would be 5 4/10, but I want the length of PR, so I have to plug it back in. So 2 times 5 4/10 plus 9 would be 19.8. Now we also can remember that the distance between a point and a line is the length of the perpendicular segment from the point to the line. So we are talking about now about distance and angle bisectors. So here's what it states. If a point is on the bisector, so we're going to take a look at the picture, we know that C is on the bisector. This is the bisector. How do we know that? Because these two angles are congruent. Then it is equidistant from the sides of the angle. Now make note that if it's equidistant from the side, those have to form 90-degree angles. So we know that we have 90-degree angles, and we have congruent angles, so it's being bisected. We know, so our hypothesis states that angle APC and angle BPC are congruent, and that point is equidistant from the sides of the angle. Therefore, we can't say AC is congruent to BC, but we can say that their lengths are equal. And then by definition of congruent segments, we could say segment AC is congruent to segment BC. So now we do the converse. The converse of the angle bisector theorem is just the opposite. If we know that point is equidistant, so now if we know that these two segments are congruent, then it is on the angle bisector. So then we would know, now notice here we have 90-degree angles as well, so that's part of our hypothesis. If we know that these are congruent and are perpendicular, then we know that angle APC is congruent to angle BPC because of the converse of the angle bisector theorem. In example 2, there's no proof, but I am going to go through the steps because if I did have these problems in a proof, you would have to show these steps. So in example A, find the measure of LM. If you would write this in proof form, you would say LM is equal to JM. And the reason would be the angle bisector theorem. The angle bisector theorem once again states that these two segments would be equal. Then by substitution, I would plug in 12.8 for JM, and we would get my answer as LM equals 12.8. Now in B, we want to find the measure of angle ABD. ABD, I'm going to mark in blue here, is that angle right there. We're given that this angle, the whole angle, is 112. So here's what we got to do. You would have to do this. This is important. We know that segment AD and segment DC are equal. We know that we have 90 degrees here. Therefore, we know that this is a perpendicular bisector. So because of the converse of the angle bisector theorem, we prove that this bisects it. Okay? Now that we know that it's a bisector, we can say the measure of angle ABD is equal to half of the big angle. Now, why can't we say that first? Because we didn't know it was a bisector. So the reason is definition of angle bisector. Definition of angle bisector would state that the one of the smaller angles is half of the bigger angle. Now I use substitution. I plug in 112, and my final answer, if we simplify it, would be 56 degrees. And the last one, the measure of angle TSU. We know that these two are congruent, so then we would have to state, because of the converse of the angle bisector theorem, we then know that SU is a bisector. So because it's a bisector, we can state that the measure of angle RSU equals the measure of angle TSU. And now by substitution, I plug in those values. So I could say RSU, which is 6z plus 14, equals 5z plus 23. That would give me z equals 9. I plug in the 9, and that would give me the measure of angle TSU as 68 degrees. Example number 3. This is the parachute problem. Each pair of suspension lines on a parachute are the same length and are equally spaced from the center of the chute. How do these lines keep the skydiver centered under the parachute? Here's your answer. It is given that segment PQ and segment RQ are congruent. Therefore, Q is on the perpendicular bisector of, which we know now is PR, by the converse of the perpendicular bisector theorem. Because this side right here and this side right here are congruent, we know that it bisects it. It's the perpendicular bisector. So since S then is the midpoint, we can then say that QS, or segment QS, is the perpendicular bisector of PR, therefore the diver remains centered under the chute. Our last example. Write an equation in point-slope form. Now remember, point-slope form is this. For the perpendicular bisector of the segment with the endpoints of -1, 6, and 3, 4. Now I've already graphed this for you. You won't have graphs for you done. But I want to write the equation of that line. That's all I want, is the equation of that line. So the two things I know, or need to know for point-slope form, is the point and the slope. So let's start with the point. This is our segment. We want to know the point at which it crosses. Now here you can see it's 1, 5. But if you didn't know that, you could find the midpoint of the red segment, segment AB. So the midpoint, if we add the x's together, that gives us negative 1 plus 3, which is 2 divided by 2, which is 1. 6 plus 4 is 10. Half of that is 5. So my midpoint is 1, 5. What's the next thing I need? I need my slope. So I find the slope of the red line. The slope of the red line, if you subtract your y's, would be 6 minus 4, which is 2. Negative 1 minus 3 is negative 4. That gives me a slope of negative 1/2. Here's the problem. That's the slope of the red line. I want the slope of the blue line. Remember, perpendicular. Perpendicular means they are opposite reciprocals of each other. So the blue line has a slope of 2. And you could check that by taking the product. The product of perpendicular slopes would be negative 1, and that does work. I now take my midpoint and my slope and I plug it into my equation. Y minus my y coordinate equals my slope times x minus my x coordinate. So my answer would be y minus 5 times 2 times x minus 1. The two vocab words are locus and equidistant.